Space is supposed to be silent, right? Just cold vacuum and nothing else. No sound, no noise, no messages. That picture is completely wrong. In radio, the universe is busy, loud, and full of activity, and you're right in the middle of it. You're on a planet orbiting the sun at about 30 kilometers per second, around 67,000 miles per hour, and all around you, there are radio waves passing by every second. But before we continue, please subscribe to the channel to give your support. Let's continue. Dead stars called pulsars are sending out regular pulses. Hydrogen gas spread between stars is constantly emitting at a precise frequency of about 1.42 gigahertz. Galaxies are glowing across a wide range of radio frequencies. When astronomers point a big radio telescope, something like the 100-meter Green Bank telescope, roughly the size of a football field, at a patch of dark sky that looks empty to your eyes, the detector does not see nothing. It fills up with spikes and patterns from thousands of separate sources. So the first thing you need to accept is simple. Space is not quiet. It is full of radio signals generated by natural processes, all layered on top of each other. That's the baseline. When you hear about a mysterious signal from deep space, that signal is not popping out of silence. It is standing out against a background that is already crowded. That alone makes these cases special, because something has to be unusual enough to be noticed on top of all this normal cosmic noise. But if space is constantly sending out radio waves from stars, gas, galaxies, and who knows what else, how do you decide what counts as a real interesting signal and what is just background clutter you can ignore? The first fight is not against the universe, it is against ourselves. Modern Earth is covered in radio frequency interference, usually called RFI. Phones, Wi-Fi, Bluetooth, GPS, satellites, aircraft radar, TV towers, power lines, cheap electronics, even cars. All of them throw radio energy into the environment. From the point of view of a radio telescope, Earth is a messy, buzzing source of interference. So astronomers put a lot of effort into cleaning this up. They know which frequency bands are used by which services. They monitor local transmitters, they install telescopes in radio-quiet zones, they track planes and satellites. When a suspicious spike appears, they check. Does it show up in all directions the telescope looks, or only when they're aimed at a specific spot in the sky? Real astronomical sources come from a fixed direction. They move only because Earth rotates and orbits, not because a plane flew by or a device switched on. Then they look at the behavior over time. Does the signal repeat? And if it does, is the repetition stable? A repeating pattern with very precise timing is often a sign of a spinning object, like a pulsar, or something in orbit. A signal that never repeats might be a one-off cosmic explosion or a weird bit of interference. Neither is boring, but they have different levels of interest. They also look at the shape of the signal in frequency space. Human technology often produces specific, narrow band patterns, like a very thin spike at one frequency. Natural processes tend to be broader and messier, but that's a guideline, not a hard rule, because some natural objects, like pulsars, can also look very clean. So you have multiple filters: direction on the sky, repetition, frequency structure, and consistency across different telescopes. Anything that survives all those filters moves into the "this is genuinely strange" category. But even after you strip away the obvious human-made junk and the easy natural explanations, there's a deeper question. How do you prove that a burst actually came from far out in space and not from something just outside the telescope or inside the electronics pretending to be cosmic? This is where one of the most important tests comes in: the effect of the interstellar medium on radio waves. Space is not completely empty. Between stars and between galaxies, there is thin gas made of charged particles, mainly electrons and protons. It is extremely dilute, but over huge distances, it adds up. When a short radio pulse travels through this plasma, different frequencies travel at slightly different speeds. Higher frequencies arrive a bit earlier, lower frequencies arrive a bit later. If you record a burst over a range of frequencies and then plot time on one axis and frequency on the other, you don't see a burst that appears everywhere at once. You see a slanted streak. High frequencies first, low frequencies trailing behind. The amount of delay between the top and bottom of the band tells you how much electron-rich material the pulse has crossed. Astronomers summarize that with a number called the dispersion measure. You can think of it as how much plasma did this thing go through on the way here. We have models for how much gas is in our own Milky Way in different directions. So if a burst is coming from within our galaxy, its dispersion measure should stay below a certain value along that line of sight. When you measure a burst and its dispersion measure is much higher than that maximum, you're almost forced into one conclusion. This thing did not just travel across our galaxy, it also crossed the much larger space between galaxies. That pushes the origin to hundreds of millions or even billions of light years away. In practical terms, the signal has traveled distances on the order of 10 to the 22 to 10 to the 25 meters, which is around 10 to the 22 to 10 to the 23 miles. That is an absurd distance, and yet your instruments can still detect a millisecond-long flash from there. Once the burst passes this dispersion test, it becomes very hard to dismiss it as some nearby glitch. It is almost certainly a real event in deep space. So if we can filter out local interference, test whether something comes from a fixed point on the sky, check its repetition, and use dispersion to prove it traveled across interstellar or even intergalactic space, why do mysterious signals keep showing up and surprising us? Shouldn't we have this under control by now? The problem is that every time we improve our tools, we expose a new layer of the universe's behavior. Build a telescope that is 10 times more sensitive, and you suddenly see fainter sources that were invisible before. Increase the field of view, and you cover a larger part of the sky at once. So rare events that only happen occasionally are now caught much more often. Improve time resolution, and you see fast bursts that were previously blurred into the noise. Take CHIME in Canada as an example. It is a set of 4 long cylindrical reflectors, each about 100 meters or 330 feet in length. It does not move like a classic dish. Instead, it uses digital processing to form many beams and watch a wide strip of sky as Earth rotates. It was built mainly for cosmology, but once it started operating, it began detecting fast radio bursts, short millisecond flashes, by the hundreds and then thousands per year, revealing that these events are happening across the sky probably tens of thousands of times every day. Now, scale that idea up to the Square Kilometre Array, the SKA, under construction in Australia and South Africa. When finished, its total effective collecting area will be about 1 square kilometer, close to 0.4 square miles. That is an enormous ear. It will be able to detect extremely faint radio sources, map hydrogen and the early universe, and almost inevitably uncover new kinds of transient signals that do not fit into any current category. So the pattern is simple but unsettling. Each major upgrade in radio astronomy hardware turns up fresh anomalies, strange pulses, odd drifts in frequency, bursts with structures we've never seen before. At first, they look like artifacts or bugs in the system. After careful checks, some of them remain, and those survivors become the new mysteries. Which leads to the real tension point in this story. If the universe is this active and our instruments keep getting sharper, what happens when one of these rare, clean signals lands exactly on a special frequency tied to the most common element in the universe, looks almost engineered, and then never repeats, no matter how hard we look? How do you deal with a signal that looks exactly like the thing you've been dreaming about, hits the perfect frequency, behaves like it's coming from deep space, and then when you go back to check, it's just gone forever? In August 1977, the Big Ear radio telescope in Ohio was scanning the sky, doing a kind of slow, patient survey. Big Ear wasn't flashy. It was basically a fixed metal structure, about 3 American football fields long overall, listening at a specific set of frequencies while the sky drifted overhead as Earth turned. The data didn't show up on a fancy screen. It printed out on paper as columns of numbers and characters. One day, astronomer Jerry Eyman is going through these printouts. Most of it is boring, just low-level background. Then he sees a sequence that jumps out, a tight cluster of characters, 6EQUJ5. That's Big Ear's way of saying the signal here suddenly shot up to about 30 times the normal noise level, then dropped back down. It lasted about 72 seconds, the exact amount of time a fixed point in the sky would sit in Big Ear's beam as Earth rotated. Eyman circles it in red pen and writes one word in the margin: wow. That 72-second burst was narrowband, concentrated in a very small frequency range, not smeared out like most natural radiation. It rose, peaked, and fell exactly how you'd expect if a radio source in space drifted through the telescope's fixed field of view. No wobbling, no obvious sign of a local glitch. It just appeared, did its thing, and disappeared. So you have a short, clean, strong signal coming near the constellation Sagittarius, behaving like it's out there in space, not near Earth. And it lights up the exact part of the spectrum that everyone in SETI had been obsessing over for years, around 1.42 gigahertz. What number itself isn't magical. What's important is what produces it. Neutral hydrogen, the simplest and most common matter in the universe, emits radio waves at that frequency through a process tied to how the electron and proton in the atom flip their relative orientation. You don't need to remember the detailed quantum physics. What matters is hydrogen does this everywhere, and it always uses the same frequency. Because hydrogen is so abundant, and because this line is so fundamental, a lot of SETI thinking said if any advanced civilization wants to announce we know physics, we know hydrogen, we know the basics, they might use that hydrogen line as a reference. It's like picking the most obvious channel, the one that any radio astronomer anywhere in the galaxy would eventually care about. So when you see a strong, stable, narrowband signal right near that hydrogen frequency, it triggers a very specific reaction. This is exactly where a deliberate hailing signal might live. It doesn't prove anything by itself, but psychologically, it hits the bullseye. You've got a nature-made universal frequency, and something just screamed on that channel for 72 seconds, then shut up. Now here's the problem. A single detection doesn't get you very far in science. You want repetition. You want follow-up. You want to say, okay, let's go back to that spot and see if it does it again. So that's what people tried to do, again and again for decades. Telescopes pointed back to that region in Sagittarius many times. Some campaigns were short. Some lasted many hours. Modern arrays, like the Very Large Array in New Mexico and others, have also checked that sky position at and around the same frequency range. The result? Nothing that looks like the original WOW signal. No strong repeats, no weaker cousins, no broadband burst that could be related. Just background. That absence is not just disappointing, it's information. If a signal never repeats, you have to place it in one of a few buckets. Maybe it was a one-off natural event, something that happened once and will not happen again in a human timescale. Maybe it was a rare kind of interference, something in or near the telescope that triggered briefly and then never showed up again. Or maybe it was a transient source with some kind of pattern we haven't recognized yet. But so far, the data points to a single spike and then silence. So, if we're being strict, we have to ask, could the WOW signal have a completely boring local explanation, and we just really want it to be special because of that wow on the page and the hydrogen frequency? People have tried to pin it on several natural or human-caused sources. One idea was comets passing near Earth, shedding clouds of hydrogen that could emit around that 1420 megahertz line. If a comet's hydrogen cloud crossed the beam in just the right way, maybe it could mimic a deep space source. Later studies tried to match comet positions and timings, but the match is not great, and Big Ear's response pattern doesn't fit that idea perfectly. Another set of suggestions pointed to satellites, reflections off space junk, or other forms of terrestrial interference. But again, the details are tricky. The WOW signal was very narrow in frequency, more like an engineered carrier than a messy reflection. Its strength changed over those 72 seconds in a way that looked like a source drifting through the telescope beam, not like a local transmitter turning on and off erratically. Also, the frequency stayed stable. It didn't jump around the way many pieces of analog electronics do when they misbehave. None of the proposed "it's just this" explanations really nails all the constraints at once. Narrow band, stable, the right time profile, the right sky position, and no obvious local culprit. So the community ended up in an uncomfortable middle ground. You can't prove it was artificial, you can't prove it was natural, you can't redetect it, and you can't fully reproduce it with known interference. That's why the WOW signal sits in a special category. Not "this is evidence of aliens," but this is a single, high-quality, unresolved data point. It refuses to close its own case. You can't build a whole theory of extraterrestrial intelligence on one event, but you also can't just erase it. It forces you to be honest about how little you can say from a one-off. And this is where the wow signal becomes more than just a weird story from the 1970s. It becomes a template. Since then, every time a new mysterious radio signal shows up, especially in SETI work, people immediately ask a set of questions that mostly trace back to lessons from WOW. Is it narrowband or broad? A truly artificial beacon is expected to be very narrowband, because that's efficient and easy to recognize. Is the frequency stable, and does it drift in a way that matches motion, like a transmitter on a rotating planet or orbiting a star? That expected Doppler drift can be a key sign. Does a signal repeat? And if it does, is the repetition tied to some orbital or rotational period? Can we see it with multiple telescopes in different locations to rule out local interference? All of that is now standard procedure because we had this one striking case where we got only a single spike and no second chance. The WOW signal taught astronomers how terrifyingly ambiguous one clean, unrepeatable event can be. It looks so organized, it lands on the special frequency, but without repetition, it remains a locked box. So now, when a new candidate pops up, something that looks too sharp, too strong, or too well-behaved for ordinary, the first reaction is not celebration. The first reaction is, we are not going to do another wow. We are going to push this thing until it either repeats or collapses into a boring local explanation. But here's the twist that pushes the tension up. What happens when a strange regular signal does repeat, over and over, so perfectly timed that the first people who saw it genuinely thought this might be someone out there trying to talk, and then it turns out to be something even more extreme and alien than that idea, but completely natural? How do you react when a signal is so regular, so clean, that the most reasonable first guess is, this is a beacon from someone intelligent, and then the universe calmly tells you, no, this is just what dead stars do? In 1967, Jocelyn Bell Burnell was a graduate student at Cambridge, going through long rolls of chart paper from a brand new radio array. Most of what she saw was messy scruff, just background variations. Then she noticed something different. A tiny section of the trace where the radio noise wasn't random anymore. It was pulsing, once every 13 seconds with absurd precision. Pulse, gap, like a metronome that never drifted. This was not a slow drift over minutes. This was beat after beat, locked in time to better than a tiny fraction of a second. For hardware in the 1960s, that was shocking. It was so unlike natural noise that the team gave it a half-joking name, LGM-1, Little Green Men 1, because if you were expecting a simple alien radio beacon, this is exactly the kind of regular pattern you would imagine, a clear on-off signal, easy to spot against the background. But scientists don't stop at the first story that sounds exciting. They kept observing. They found more of these pulsing sources in different parts of the sky, each with its own stable period. At that point, the single alien lighthouse idea starts to break. The cleaner explanation is this is a new type of astrophysical object. Eventually, putting together all the clues, the pulse timings, the energy, the spectra, the positions, they landed on the real answer. These were neutron stars, the collapsed cores of massive stars that had exploded, now about 20 kilometers across, roughly 12 miles, spinning so fast that their surface is moving at a significant fraction of the speed of light. That object then keeps almost the exact same spin period over years, with tiny, predictable changes. Astronomers use these pulsars as tools. By timing their pulses precisely, they can map how gravity from other objects, like passing stars or clouds of gas, tugs on them. They can use arrays of pulsars spread across the galaxy as a sort of giant detector, looking for slow, large-scale distortions caused by gravitational waves from supermassive black hole pairs. You're basically turning dead stars into a timing network that stretches over thousands of light years. So here's the important shift in thinking. If nature can build clocks this good from nothing but collapsed stars and magnetic fields, what does that do to your instinct that regular and precise automatically means artificial? This is the core lesson of pulsars. Regular does not equal artificial. The pulses look like a message at first, but they're not encoding anything. They're just a lighthouse beam of a rotating magnetic object. The physics is extreme, but it is still just physics. No engineering, no intention. When you see that, it should change how you approach every new signal that looks too perfect. The universe can fake designed patterns using nothing but gravity, nuclear matter, and magnetism. And even these perfect clocks are not completely flawless. Sometimes the timing of a pulsar jumps. Out of nowhere, the spin rate increases by a tiny fraction, maybe a part per million, and then slowly settles back to its previous behavior. These are called glitches. On the chart, they look like a sudden step in the pulse arrival times. What could cause that in an object this dense and compact? The leading ideas involve starquakes, where the solid crust of the neutron star suddenly cracks and rearranges, or the interaction between the superfluid interior and the outer layers suddenly changes, dumping angular momentum into the crust. You do not see the surface, but you see the effect at a distance of thousands or tens of thousands of light years. When those pulses arrive a bit early or a bit late, you're literally watching the internal structure of a dead star shift in real time. Remember the speeds involved. The surface of a fast pulsar can be moving at hundreds of kilometers per second. That's hundreds of thousands of miles per hour. A tiny change in rotation frequency, measured from Earth, is your only clue that something violent happened in that star's interior, an event you will never see directly, only through timing. That is how sensitive these cosmic clocks are. This whole story forced astronomers to update their instincts. Before pulsars, a periodic, very clean signal would have been immediately flagged as "this might be a beacon." After pulsars, you have to ask a different question first. What kind of extreme astrophysical object could produce this without any intelligence at all? So now, when a new mysterious periodic signal shows up, the first checklist is not, "is this aliens?" It is, "could this be a neutron star? A white dwarf? A binary system? Some new kind of compact object?" The bar for calling something a technosignature is much higher, because you've already seen nature do this kind of precision on its own. And that mindset is exactly what you need for the next level of weird signals. The ones that are not steady pulses like pulsars, but unpredictable, ultra-short flashes that come from way outside our galaxy, burn as bright as whole galaxies in radio for 1,000th of a second, and then vanish, leaving nothing but a sharp spike in the data and a huge dispersion measure that screams, "this crossed billions of light years." If pulsars were the first case where a "this must be artificial" signal turned out to be natural, what do you do when you start getting hit by millisecond-long radio bursts from deep space, so energetic they should be impossible from such short events, and you have no solid idea what's causing most of them yet? How much can the universe really do in 1 millisecond, in 1,000th of a second that you would normally just ignore? In 2007, a team was going through old data from the Parkes Radio Telescope in Australia. This was not live observing, this was archival cleanup, the kind of work where you mostly expect to find nothing new. Buried in that data, they found a single sharp radio flash that lasted about 1 millisecond. That's shorter than a camera flash, shorter than a blink. If you were listening in real time, you would never notice it. But when they measured how that flash arrived at different frequencies, the dispersion was huge. The low frequencies were delayed so much compared to the high frequencies that there was no way to explain it with gas inside our own Milky Way, not along that line of sight. The amount of plasma implied by that delay told you this thing did not just cross our galaxy, it traveled through the space between galaxies as well. So the simplest interpretation was the source was probably billions of light years away. Now, combine those two facts: distance on the order of billions of light years, duration about 1,000th of a second, and then that tiny slice of time, the burst carried as much energy in radio as our sun emits over many days. A distant galaxy's worth of normal radio output squeezed into a blink, and then it's gone. At first, this looked like a weird one-off, a curiosity, but the signal did not match any known instrumental glitch, and the dispersion curve looked exactly like a real deep space pulse. So the question became, is this some unique freak event, or are we seeing the first example of a whole new class of phenomena that we've been missing because we weren't looking with the right tools? That question was answered brutally once we built instruments that could watch a wide piece of sky all the time with high time resolution. That is where CHIME comes in. CHIME in British Columbia is a different kind of radio telescope. Instead of a single round dish that you steer, it uses 4 long cylindrical reflectors, each about 100 meters long, roughly 330 feet. It does not move mechanically, it stares at the sky, and as Earth rotates, the sky drifts over it. Digital processing forms many simultaneous beams so it can monitor a huge strip of sky across the 400 to 800 megahertz band. Originally, CHIME was built to study how the universe is expanding by mapping hydrogen, but once it started recording high time resolution data, it turned out to be absurdly good at catching short radio flashes. Suddenly, those rare-looking bursts were not rare. CHIME began detecting hundreds of fast radio bursts per year, then more, and that's with just one instrument in one place, operating in one frequency range. From that, you can estimate how many FRBs must be happening across the whole sky, in all directions at all times. The numbers come out to at least tens of thousands of bursts per day, maybe more. That means that right now, while you're watching this, there are FRBs going off in random directions all over the universe, millisecond flashes that you will never notice because only a tiny fraction line up with Earth and hit a telescope at exactly the right moment. Once you know these bursts are common, the next question is obvious. Are they all the same kind of event, or are there different species of FRBs hiding inside this flood? One of the first big clues came when astronomers found an FRB that did not just happen once and vanish. FRB 121102, discovered in 2012, was later caught repeating, not just once, but hundreds of times from the same patch of sky. We eventually linked it to a small, faint dwarf galaxy about 3 billion light-years away. This object sends out burst after burst, sometimes in clusters, sometimes quiet for a while, then active again. Meanwhile, many other FRBs are one and done. We see a single burst with no repeats even after many hours of follow-up. It's possible they repeat on timescales or in patterns we haven't caught yet, but as far as our instruments can tell, they fire once and then go silent. That split, repeaters versus apparent one-offs, is a huge deal. It suggests we're dealing with a single engine. Maybe the repeating FRBs are powered by some kind of compact object that can flare over and over, like a young magnetar with an unstable magnetic field. Maybe the non-repeaters are tied to catastrophic events, like the collapse of a massive star to a black hole, or the merger of 2 neutron stars, events that only happen once for that system. You now have to build models that can produce insanely bright millisecond-long radio bursts, sometimes repeatedly, sometimes only once, and they have to match the energy scales, the dispersion measures, and the environments we see. That last part, the environments, is where the next big step comes in, actually locating FRBs precisely in the sky. Early FRBs were detected with single dishes like Parkes, which are great ears but have poor angular resolution. You know roughly where the burst came from, but not enough to nail down a specific host galaxy. Interferometers, like ASKAP in Australia or the Very Large Array in New Mexico, change that. They use many dishes spread over kilometers, sometimes tens of kilometers, and combine their signals to get very sharp positions. With these arrays, astronomers have managed to localize several FRBs to precise spots inside specific galaxies. Some are found in regions with intense star formation, packed with young, massive stars. Others show up in quieter areas, in the outskirts of galaxies. The host galaxies themselves can be small dwarfs, Milky Way-sized spirals, or something in between. This environmental information acts like a constraint. A model that says all FRBs come from young magnetars born in recent supernova explosions has to explain why some FRBs sit in regions where star formation is low. A model that ties FRBs to mergers of old neutron star pairs has to explain why some are deep inside vigorous star-forming zones. The data forces theorists to stop guessing in the abstract and actually match real locations, real host types, real local conditions. But for a long time, even with all this, FRBs were still detached from any specific object. You could say probably something like a magnetar, but you could not point to a known source and say, this one right here did it. That changed in 2020, inside our own galaxy. In April 2020, a known magnetar in the Milky Way, called SGR 1935 plus 2154, suddenly produced a radio burst that looked very similar to a fast radio burst, just weaker because it was so much closer. Radio telescopes caught a bright millisecond-scale pulse, and high-energy satellites saw X-ray activity at the same time. When you scale that event up to extragalactic distances, its energy lands right in the range of what we see as normal FRBs from other galaxies. This was the first solid direct link between an FRB-like burst and a specific physical object, an ultramagnetized neutron star. A magnetar is a neutron star with an insane magnetic field, roughly between 10 billion and 100 billion Tesla at the surface. For comparison, the strongest steady magnets humans can build are in the tens of Tesla. You are looking at fields roughly 10 billion times stronger than anything we can build. At those field strengths, normal matter physics starts to break. Atomic structures are distorted, electron motion is completely dominated by the magnetic field, and the vacuum itself behaves differently. Space near a magnetar is not a calm void. It's more like an overcharged environment where small changes can release huge amounts of energy. This is not just a stronger version of a pulsar, it's in a different regime. So you have a compact object, city-sized, with a mass similar to the sun, wrapped in a magnetic field so strong that if you somehow put one halfway to the moon, its field would noticeably affect electronics here on Earth. That is the baseline, before it even does anything violent. The next question is, how does something this extreme actually lose energy? And what does that look like when it snaps? Magnetars are known for sudden, intense flares in X-rays and gamma rays. These are not gentle variations, they are explosive events. One of the most dramatic cases was in 2004 from a magnetar called SGR 180620, about 50,000 light-years away, on the far side of the Milky Way. Detectors around Earth saw a huge spike in gamma rays, strong enough to briefly saturate instruments designed to watch entire galaxies. For a fraction of a second, that one magnetar outshone the rest of the Milky Way in gamma rays. When you convert that into energy, you get something comparable to what the sun would radiate over about 100,000 years, dumped out in a moment, focused into high-energy photons. And remember, this happened from tens of thousands of light-years away, and it still hit us that hard. The leading idea is that these flares are caused by starquakes and magnetic reconnection. The solid crust of the magnetar is under constant stress from the twisted magnetic field. At some point, the stress becomes too high, the crust cracks or shifts, and the magnetic field lines rearrange violently. Similar in spirit to a solar flare, but on a much larger scale. The result is a burst of radiation and particles that escapes into space. Now, connect that to fast radio bursts. We know magnetars can produce giant high-energy flares. We also know that when magnetic fields of this strength snap and reconnect, they can accelerate electrons to near light speeds. Those electrons moving through the magnetic field can generate what is called coherent radio emission, where many particles radiate in sync, boosting the brightness far beyond what you'd get from random emission. It's like a natural maser, a radio version of a laser, but on the scale of a star. So you have a connection. At least some FRBs can be produced by magnetars throwing magnetic tantrums. That does not solve the whole FRB puzzle, but it gives you a concrete anchor. We're not just guessing in the dark anymore. We have at least one example where we can say, this burst came from that object in our own galaxy. But that answer immediately opens the next question. If magnetars can fire off bursts this powerful and their magnetic fields are this extreme, what exactly are these objects doing inside? What kind of physics is going on in a star so dense that a teaspoon of its material would weigh more than 1 billion tons, and so magnetized that it could erase data from a hard drive from halfway to the moon? How do you even classify an object that is so intense it could erase every hard drive on Earth if you put it a few light years away, and yet astronomers still just call it a kind of dead star? Start with a neutron star. That is already extreme. Take something with about 1 to 2 times the mass of the Sun, compress it into a sphere about 20 kilometers across, around 12 miles, and you get matter so dense that a teaspoon of it would weigh around 1 billion tons, roughly 1 trillion US tons. Gravity there is ridiculous, hundreds of billions of times stronger than on Earth. Now, take that already insane object and crank its magnetic field up by a factor of around 1,000 compared to a typical pulsar. You end up with a magnetar. At the surface, the magnetic field can reach something like 100 billion Tesla. For context, the strongest steady magnets humans manage in the lab are in the tens of Tesla. You are looking at fields roughly 10 billion times stronger than anything we can build. At those field strengths, normal matter physics starts to break. Atomic structures are distorted, electron motion is completely dominated by the magnetic field, and the vacuum itself behaves differently. Space near a magnetar is not a calm void. It's more like an overcharged environment where small changes can release huge amounts of energy. This is not just a stronger version of a pulsar, it's in a different regime. So you have a compact object, city-sized, with a mass similar to the Sun, wrapped in a magnetic field so strong that if you somehow put one halfway to the Moon, its field would noticeably affect electronics here on Earth. That is the baseline, before it even does anything violent. The next question is, how does something this extreme actually lose energy? And what does that look like when it snaps? Magnetars are known for sudden, intense flares in X-rays and gamma rays. These are not gentle variations, they are explosive events. One of the most dramatic cases was in 2004 from a magnetar called SGR 180620, about 50,000 light-years away, on the far side of the Milky Way. Detectors around Earth saw a huge spike in gamma rays, strong enough to briefly saturate instruments designed to watch entire galaxies. For a fraction of a second, that one magnetar outshone the rest of the Milky Way in gamma rays. When you convert that into energy, you get something comparable to what the Sun would radiate over about 100,000 years, thumped out in a moment, focused into high-energy photons. And remember, this happened from tens of thousands of light years away, and it still hit us that hard. The leading idea is that these flares are caused by starquakes and magnetic reconnection. The solid crust of the magnetar is under constant stress from the twisted magnetic field. At some point, the stress becomes too high, the crust cracks or shifts, and the magnetic field lines rearrange violently. Similar in spirit to a solar flare, but on a much larger scale. The result is a burst of radiation and particles that escapes into space. Now, connect that to fast radio bursts. We know magnetars can produce giant high-energy flares. We also know that when magnetic fields of this strength snap and reconnect, they can accelerate electrons to near light speeds. Those electrons moving through the magnetic field can generate what is called coherent radio emission, where many particles radiate in sync, boosting the brightness far beyond what you'd get from random emission. It's like a natural maser, a radio version of a laser, but on the scale of a star. A burst like that naturally falls into the right timescale, milliseconds. The magnetospheric region involved might only span a few hundred to a few thousand kilometers, a few hundred to a few thousand miles. So light crossing time is short. You get a narrowly timed flash, enormous brightness, and a mechanism that can repeat whenever the magnetic stresses rebuild. When we saw the 2020 burst from SGR 1935 plus 2154 in our own galaxy with an FRB-like radio flash plus X-rays, it lined up almost perfectly with this picture. So magnetars tick a lot of boxes for FRBs. They are compact, highly magnetized, capable of rapid energy release, and can, in principle, flare multiple times over their active lifetimes. That pushes them to the front of the suspect list. But if they are really behind a big fraction of FRBs, we should see certain signatures in the data. First, location. Magnetars are thought to form from very massive stars that explode as supernovae, and massive stars do not live long. They stay near where they were born, in star-forming regions full of gas and young stars. So if FRBs are mostly magnetar-driven, many of them should be in or near active star-forming regions in their host galaxies, not randomly scattered. When we localize FRBs, quite a few do land in such regions, especially repeaters, which supports the magnetar idea. But not all of them do, and that is attention. Second, polarization. Strong magnetic fields leave a fingerprint on radio waves. They affect how the polarization, the orientation of the wave's electric field, rotates as the signal passes through magnetized plasma. If FRBs are coming from environments with extreme fields, we expect to see high degrees of polarization and strong, sometimes variable rotation of that polarization angle as a function of frequency. Many FRBs do show exactly this kind of behavior, indicating they live in magnetized environments. Others are less polarized or show different patterns, which again suggests multiple types of sources or environments. Third, the detailed structure of the burst. When you look at high-resolution FRB data, the bursts are often not just single smooth blips. They can break into multiple subbursts, drifting in frequency over time, with complicated internal shapes. Models of magnetar magnetospheres can produce these kinds of features by having different emission regions light up at slightly different times and frequencies. Observationally, a lot of FRBs show complex time-frequency structure that fits comfortably with magnetar-based scenarios. But like before, not every burst is a perfect fit. So magnetars explain many patterns, but not all, and that leads to the big statistical headache, the rate problem. If you estimate how many FRBs occur over the whole sky, you get something like tens of thousands per day above current detection thresholds. Even if each individual magnetar can produce many bursts over its active lifetime, you still need enough magnetars being born and staying active to keep that rate going. That links FRBs directly to how often massive stars form and explode in the universe. We do have estimates of supernovae rates and magnetar birth rates from observations of nearby galaxies and from theory. When you plug those into simple models, how many magnetars per galaxy, how long they stay highly active, how often they flare, you can make the numbers for FRBs almost work. But it is tight. In some scenarios, you need magnetars to be extremely active for a short time after they are born, firing off many FRB-like bursts in a relatively brief window, then going quiet. In others, you need more magnetars or extra channels like mergers to fill the gap. This is why a lot of researchers suspect magnetars are a big part of the story, maybe the dominant engine for many FRBs, especially the repeaters, but probably not the whole story. There may be other kinds of compact objects contributing, or entirely different mechanisms for some subclasses. The data is pushing us toward a mixed population. And that brings us to an uncomfortable point. If you already have neutron stars, pulsars, and magnetars generating all kinds of wild signals, and they can trick you into thinking this looks artificial when it's just physics, how do you make sure you are not being fooled the other way? Seeing something you think is cosmic and exotic when it's actually coming from something as mundane as a device in the next building. How can a billion-dollar eye on the universe be beaten by a cheap kitchen appliance next door? At Parkes Observatory in Australia, a 64-meter radio dish, about 210 feet across, was hunting for fast radio bursts and other transients. In its data, astronomers kept seeing strange blips, short bursts that looked a lot like FRBs at first glance. They were millisecond scale, they had some dispersion, they weren't obviously tied to a known satellite or radio source. These events got a nickname, perytons. On paper, perytons were exciting. They had the right sort of timescale, very fast, and they showed a curve in frequency that had some similarity to real FRB dispersion. They weren't just flat, simple glitches. If you were eager to find more FRBs, this looked like a hint that you were catching a bunch of them, maybe from all over the sky. But something was off. The perytons didn't quite match real FRBs. Their dispersion patterns were a bit weird, not following the exact mathematical relationship you expect from propagation through interstellar plasma. Their sky distribution also looked suspiciously non-random. And then someone noticed a pattern that had nothing to do with astrophysics. The times of these events were clustering around midday, especially near lunchtime. That is not when the universe decides to send more bursts. That is when humans decide to eat. So the team started thinking on a different track. What if these signals weren't cosmic at all? What if they were coming from some piece of hardware at the site, something that was active during office hours and quiet at night? Eventually, they traced the perytons to a very ordinary source, microwave ovens in the nearby buildings. When someone cooked food and then opened the door before the timer reached zero, the magnetron inside the microwave, the device that generates the heating radio waves, would shut down in a messy way. That sudden interruption leaked a short burst of radio noise out into the environment. The timing and frequencies of that burst were just right to get into the telescope's side lobes and show up as a fast, dispersed-looking signal. So the FRB-like blips that have been puzzling people for years turned out to be the side effect of people reheating leftovers and being impatient. You had a 64-meter radial telescope, a serious piece of scientific infrastructure, being tricked by a box in the staff kitchen. That's funny, but it's also brutal. It shows you how easy it is to fool yourself when you're dealing with faint, rare events and sensitive instruments. You can be staring at a dish designed to catch signals from billions of light years away and still be dominated by something happening 100 meters away, 300 feet away, because the telescope doesn't care about your intentions. It just records whatever radio energy lands on its receiver. This is where the humility lesson kicks in. After perytons, every mysterious signal claim has to clear a much higher bar. You cannot just see something that looks odd and shout, "New phenomenon." You have to treat your entire site, your hardware, your cables, your software, your surroundings as suspects. That means checking for the boring stuff first. Is there construction nearby using noisy equipment? Are there aircraft overhead with new radar systems? Are there satellites transmitting in sidebands you didn't know about? Did someone plug in a cheap device with a bad power supply that sprays interference? Are the observatory's own systems, like network links, local oscillators, or digital electronics, producing periodic noise that leaks into the data? Modern radio observatories have harsh RFI protocols. They maintain catalogs of known interfering sources. They log airplane tracks, they track satellites, they monitor the spectrum even when they're not doing astronomy. They cross-check events against this interference database before even thinking of calling something interesting. But there's an even cleaner way to tell Earth apart from space, and that is to use the planet itself as part of the test. If a signal comes from a local source, it should not show up the same way at two observatories that are thousands of kilometers apart, thousands of miles apart, especially if they are not sharing infrastructure. So for serious candidates, astronomers try to get multi-station confirmation. If CHIME in Canada sees a fast burst at a specific time and frequency, and that almost the same time another telescope on a different continent sees a similar event from the same direction with the correct slight time offset due to the light travel time across Earth's diameter, that's huge. It tells you that the signal is not just some local glitch at one site. For ultra-fast events like FRBs, arrival times matter a lot. If two observatories are, say, 8,000 kilometers apart, about 5,000 miles, the maximum difference in arrival time for a signal from far away is about 27 milliseconds, the time it takes light to cross that separation. If the bursts arrive with exactly the offset you expect for a distant source, that's strong support for a cosmic origin. If they arrive out of sync or only show up at one site, that points back to local interference. This multi-station test doesn't just apply to radio. It's now standard in gravitational wave astronomy too. LIGO and Virgo use multiple detectors to rule out local disturbances. The same logic is spreading through all rare events fields. If you can't see it in more than one place, you have to be very cautious. So why should you, watching a video about space, care about a story that boils down to microwave oven trick scientists? Because it tells you how you should react when you see headlines about mysterious signals from space. Your first question should not be, is this aliens? It should be, did they beat the peryton test? Did they rule out obvious local sources? Did they check for microwave-style interference, faulty cables, ground reflections, aircraft, satellites, software bugs, clock errors in the timing systems, anything that could fake a pattern? Did more than one observatory see it in more than one way? Real mysteries survive that kind of abuse. They stay put when you change telescopes, when you move to a different continent, when you alter observing frequencies, when you tighten your RFI masks. Fake mysteries die in those tests. They turn out to be bad connectors, misconfigured equipment, or yes, somebody's lunch. The peryton story is basically a permanent warning label on the field of transient astronomy. It says you are working at the edge of what your instruments can do, and the universe is not the only thing that can surprise you. That doesn't make the real cosmic signals less impressive. It makes them more impressive, because they're the ones that survive all of this skepticism. But there's another twist. Not every signal from space is a radio blip. Sometimes the weird thing is not a spike in a radio spectrum, it's a slow, irregular dimming of a star's light over days or weeks that does not look like any normal planet transit or stellar cycle. And when that kind of anomaly showed up, people did exactly what you'd expect after all these stories. They jumped straight to one of the wildest possibilities. Maybe this is not just nature, maybe this is a sign of something built. So what do you do when a perfectly normal-looking star starts dimming in a way that does not match any of the usual explanations, and the phrase alien megastructures hits the news before the data is fully understood? How do you react when a completely normal-looking star starts losing a fifth of its light for no clear reason, and doesn't do it on any schedule you can predict? Kepler, the space telescope, was built to do one main job: stare at thousands of stars and measure their brightness very precisely over time. The idea was simple. When a planet passes in front of its star, it blocks a tiny fraction of the light. For something like Jupiter crossing a sun-like star, that drop is about 1%. For an Earth-sized planet, it's more like 0.01%. Kepler was tuned to catch dips like that. Then there was KIC 8462852, now better known as Tabby star. Its light curve did not behave. Instead of neat, repeating dips with a clear period, its brightness dropped in messy, irregular ways. Sometimes the star dimmed by a few percent, sometimes by as much as 22%. That's not a small shadow. To block that much light, you'd need something huge, larger than any known planet, passing in front of the star. And it wasn't repeating cleanly. The dips were asymmetric. The star faded and recovered in shapes that didn't match a simple sphere crossing the disk. The timings were aperiodic, not on a stable schedule. Sometimes the dips came in clusters. Sometimes the star sat at normal brightness for long stretches, then suddenly changed. If you tried to fit a normal planet transit model to it, it just didn't work. So you have a star about 1,500 light-years away, roughly 14 quadrillion kilometers, or around 9 quadrillion miles, and from that distance, it's acting like something big and complicated is moving between you and it. And whatever that something is, it's not following the rules you expect from planets. Once you have a star that refuses to fit the simple models, your brain is going to jump to the most dramatic idea that still uses known concepts. And that's exactly what happened. One early speculative suggestion was not one giant object, but a swarm. The idea was maybe you're seeing the effects of a large number of artificial structures in orbit, something like a partial Dyson swarm. That's the concept where a very advanced civilization surrounds its star with energy collectors to grab a big fraction of its output. You don't need a solid shell. A cloud of many separate units would already change the light in strange ways. The phrase alien megastructures hit the discussion, and once that language was out there, it spread fast. Headlines grabbed it. Articles skipped over all the caveats, all the "this is wildly speculative," and focused on astronomers find possible alien structure. It sounded cinematic, it sounded simple, and it completely overshadowed the quiet, less flashy explanations that were also on the table. Serious teams took the possibility seriously enough to test the easiest version of it. If there really is a very advanced civilization doing heavy engineering around the star, maybe they're also transmitting in radio. Observatories like the Allen Telescope Array pointed at Tabby star, listening for narrow band beacons, obvious artificial tones, anything above their sensitivity limits. The result, so far, is nothing. No clear radio technosignature. So now you're back to the hard work. If it's not obviously broadcasting in radio, and we can't just jump to megastructures, what natural process can block 20% of a star's light in weird changing patterns without glowing strongly in other wavelengths? Follow-up observations looked at Tabby's star in different bands, not just visible light, but also infrared. That's important because if you surround a star with solid structures or you dump a lot of material around it, it will usually absorb starlight and re-emit that energy at longer wavelengths, especially in the infrared. You'd expect a kind of excess infrared glow. What people found instead was more consistent with dust. The dimming was stronger in blue light and weaker in red and infrared, which is what you'd expect if small dust grains are blocking the light. Dust particles scatter and absorb short wavelengths more efficiently than long ones. The data started to line up with a picture where there are complex, uneven clouds of dust, maybe from comets, maybe from collisions of larger bodies, crossing the line of sight in irregular ways. It's not a perfect, neat model. It's messy. You might need multiple populations of dust at different distances with different grain sizes. You might need long-term changes in the star's surroundings or slow secular dimming over decades, layered on top of short-term dips. But when you compare messy dust and debris in a complicated system to a civilization building city-sized panels and moving them around all the time, dust wins on probability. The universe already makes dust and destroys comets. We know that happens. Even if the final explanation is still being refined, the general direction is clear. Natural, if complicated, processes involving dust and debris can explain the main features without calling on megastructures. The star is still weird, just not sci-fi cover art weird. So why treat this as a signal at all if there's no radio beacon, no obvious pattern that looks like a code? Because the signal here is not sound or pulses, it's the brightness curve itself. What Kepler recorded is a time series, brightness versus time, measured again and again for years. That curve is a data stream. Every dip, every recovery, every long-term trend is information about whatever is crossing the star or changing in its environment. You are effectively reading a shadow play from 1,500 light-years away with no direct image, only a graph that rises and falls. Tabby star forced astronomers to treat weird light curves as a valuable search space, not just noise. If you only look for clean, periodic dips, you'll find lots of nice planets, but you'll miss systems that are doing something more chaotic. Debris disks, swarms of fragments, tilted structures, partial rings, even scenarios we haven't imagined yet, can all write their stories into the brightness record. And there's a deeper pattern here that you'll see again and again as we go through mysterious signals. A strange behavior shows up. Nature gives you something you didn't forecast. Humans immediately jump to the most dramatic narrative that fits the data loosely, often involving aliens or new physics. As more data is collected from more instruments and more wavelengths, the explanation shifts toward a more grounded picture. Still interesting, still often extreme, but built from known ingredients. Tabby's star is a clean case of that arc. At first, alien megastructures dominates the conversation. Later, multi-wavelength observations point to dust, maybe comets, maybe collisions. The system is still unusual, the details are still being debated, but the story is moving from "this might be a deliberate construction" to "this is a complex astrophysical mess we don't fully understand yet." The drama decreases a bit, but the science deepens. And that meta lesson feeds back into how we handle every new anomaly. You can't ban wild ideas, they help you think more broadly, but you can't stop at them either. You have to keep watching, keep collecting data, and accept that most mysteries, over time, migrate toward explanations that are less cinematic but still push our understanding forward. Now, take that way of thinking and scale it up. Instead of one star with a weird brightness curve, ask what happens when the entire sky glows with a faint microwave signal that seems almost perfectly smooth, and then tiny ripples in that glow turn out to encode the structure of the whole universe, its age, its contents, its geometry. How do you mistake the afterglow of the Big Bang for a bit of annoying static that you keep trying to get rid of? In 1964, Arno Penzias and Robert Wilson were working with a 6-meter, about 20-foot, horn antenna in New Jersey. It was built for satellite communication tests, not cosmology. They were trying to calibrate it to understand and remove every source of unwanted noise. No matter which way they pointed the antenna, they kept seeing an extra signal, a microwave hiss that looked like a temperature of roughly 3 Kelvin above absolute zero. Absolute zero is 0 Kelvin, the point where, in classical terms, all thermal motion stops. So a 3K signal means the antenna was seeing something as if it were immersed in a very cold bath of radiation, just a few degrees above that limit. They suspected everything: warm electronics, the ground, the atmosphere, even the metal of the horn. They even climbed into the antenna, cleaned out pigeon droppings, and removed the birds because they thought maybe the mess was causing extra noise. Nothing changed. The noise stayed. It came from every direction, at all times, with the same temperature. When they talked to cosmologists at nearby Princeton, they learned that people had predicted exactly this kind of background as a consequence of a hot Big Bang. The idea was that the universe was about 380,000 years old. It cooled enough for electrons and protons to combine into neutral atoms. At that moment, light could finally travel freely. That fossil light should have stretched into the microwave range as the universe expanded. The annoying 3K static in the horn turned out to be that fossil light, the cosmic microwave background, the CMB. It is literally the leftover radiation from the early universe, still filling all of space, including the room you're in right now. The next question is, what exactly does this background look like when you measure it in detail, and how perfect is it? When you measure the CMB across a range of microwave frequencies, you get a spectrum that is insanely close to what's called a black-body spectrum. A black-body spectrum is the pattern of light emitted by an ideal object that absorbs and re-emits all radiation perfectly, and it depends only on temperature. For the CMB, that temperature is about 2.725 Kelvin. The match is ridiculously precise. Deviations from the ideal black-body shape are at the level of a few parts in 100,000. In other words, if you scaled the main curve up to a height of 100,000 units, the wiggles away from that shape would be only 1 unit tall. That is one of the most precise agreements between theory and observation in all of physics. This radiation has wavelengths in the range of roughly 1 to 10 millimeters, about 0.04 to 0.4 inches. It comes at you from all directions. If you could see microwaves with your eyes, the entire sky would glow with this smooth, cold background. You are permanently bathed in it, day and night. It is the cleanest, most uniform noise field we have ever measured. But the most important information is not in the smooth part. It's in the tiny deviations from smoothness. Space missions like COBE, WEMAP, and Planck took the next step. They didn't just measure the average 2.7 K temperature, they mapped how that temperature changes very slightly across the sky. The variations are tiny, on the order of a few tens of microkelvin, which is about 0.0001 Kelvin. To detect them, you need instruments with extreme stability and sensitivity. Those small hot and cold spots are not random decoration. They represent regions in the early universe where the density was slightly higher or lower than average. Slightly denser patches had a bit more gravity, so over billions of years they grew into galaxies, clusters of galaxies, and the large-scale web of structure we see today. Slightly less dense patches became the cosmic voids, the huge empty regions between filaments. By analyzing the statistics of these temperature fluctuations, how big they are, how often they repeat at different angular scales on the sky, cosmologists can extract the basic parameters that describe the universe. Things like how fast it was expanding back then, how much ordinary matter there was, how much dark matter, how much radiation, and what kind of initial fluctuations the Big Bang produced. You're taking a noisy microwave map and turning it into a full set of numbers that describe the universe's initial conditions. This is the opposite of a one-off anomaly like the wow signal or a single FRB. The CMB is not a blip you saw once and might have misinterpreted. It is an all-sky, persistent signal that has been measured, remeasured, and checked by multiple experiments over decades. Different instruments agree. Different methods agree. When you plug it into the equations of Big Bang cosmology, it fits with absurd precision. That's why the CMB is a benchmark. Any new, exotic idea about the universe has to respect it. If you invent a model where the universe is much younger or much older or has wildly different contents, you have to show how that model still produces the same almost perfect 2.7K black body background with the same tiny fluctuation pattern. If you can't, your idea is probably wrong. So when someone proposes that a mysterious signal requires a completely new kind of physics that changes the expansion history of the universe or radically alters how matter and radiation interacted in the early universe, the first question is, does this wreck the CMB fit? If it does, it is in serious trouble. That doesn't mean you can never modify the standard picture, but it means the modifications must be subtle enough to leave this very precise signal mostly intact. From the CMB, combined with other data, we get a consistent picture. The universe is about 13.8 billion years old. Only roughly 5% of its energy content is normal matter, the stuff that makes stars, planets, and you. About 27% is dark matter, which gravitates but does not emit light. Around 68% is dark energy, a component that drives the accelerated expansion of the universe. Those numbers are not guesses, they are tightly constrained by how well models match the CMB maps. This is what sharpening the mystery filters means. Before the CMB maps, you could invent wild models for strange signals with few hard constraints. Now, any explanation you give for a new anomaly has to fit inside a framework where we already know the age, composition, and overall geometry of the universe to high precision. You can't casually invoke huge changes in fundamental constants or dramatic extra forms of energy without breaking the CMB. So you have two levels now. On the one hand, rare, sharp signals like FRBs, pulsars, and the wow event, which raise focused local questions. On the other hand, this giant, nearly perfect microwave background which pins down the global rules. Any story you tell about a new, mysterious signal has to be compatible with both the local behavior and the global constraints. But radio waves and microwaves are only part of the picture. Not every messenger from deep space is electromagnetic. Some of the most extreme events in the universe send out particles that barely interact at all, flying straight through stars and planets like they're almost not there. Or they hurl single atomic nuclei at energies that make our best accelerators look weak. Those ghostly neutrinos and ultra-high energy cosmic rays are signals too, just written in a different language, one that forces you to build detectors out of Antarctic ice and entire patches of atmosphere. How do you listen to the universe using particles that can cross an entire galaxy, pass straight through Earth, and almost never leave a trace? Neutrinos are like that. They have a tiny mass, close to zero, and they barely interact with normal matter. A neutrino can go through a light year of solid lead and still probably not hit anything. Yet, stars, supernovae, and nuclear reactions make them in huge numbers. Right now, trillions of them are going through your body every second, and you feel nothing. In 1987, a star exploded in the Large Magellanic Cloud, a small companion galaxy to the Milky Way, about 168,000 light-years away. We call that explosion SN 1987A. Before the light from the supernova reached us, neutrino detectors on Earth picked up a burst, only about 24 neutrinos total, spread across different experiments. That sounds tiny, but those particles had traveled around 168,000 years, crossing about 1.6 times 10 to the 21 meters of space, roughly 10 to the 21 miles, then straight through Earth itself to land in tanks of water and other detectors buried underground. Those 20-something neutrinos were a signal. They told us that deep inside that collapsing star, when the core turned into a neutron star, a huge amount of energy was dumped into neutrinos, and a tiny fraction of them happened to hit Earth and leave detectable flashes. That was the first clear confirmation that supernova cores really behave the way our models said. One tiny burst, but it carried direct information from the heart of a star that had just torn itself apart. But neutrinos from SN 1987A were low energy by the standards of the universe's really violent events. If you want to catch the most extreme neutrinos, you have to build something on a ridiculous scale. That's where IceCube comes in. IceCube is a neutrino observatory at the South Pole. Instead of a tank, it uses a cubic kilometer of clear Antarctic ice, about 0.24 cubic miles. Engineers drilled deep holes and lowered strings of light sensors, thousands of them, into the ice, up to about 2.5 kilometers down, around 1.5 miles. The ice is so transparent that when a high-energy neutrino happens to hit a nucleus in the ice and produce a charged particle moving faster than light moves in that medium, it creates a faint flash of blue light, called Cherkonov radiation. The sensors pick up that flash. Most of the time, IceCube sees background events from cosmic rays hitting the atmosphere, but occasionally it catches neutrinos with energies above 1,000,000,000,000 electron volts, 1 tera electron volt, and sometimes much higher. For comparison, the Large Hadron Collider in Europe accelerates protons up to a few trillion electron volts. Some IceCube neutrinos carry more. That means nature is accelerating particles to energies that match or beat our biggest machines. In 2017, IceCube detected one especially high-energy neutrino, with energy around the few hundred trillion electron volts. This one event triggered an alert broadcast to observatories around the world. Telescopes looked in the direction IceCube inferred for the incoming neutrino. They found a flaring blazar there, a type of active galaxy where a supermassive black hole is launching a jet of particles almost directly towards us, at near light speed. That alignment suggested the neutrino came from that jet, giving us the first strong link between a specific neutrino and a specific astrophysical object. So that one neutrino, just one particle, was a signal from a black hole engine billions of light years away, delivering direct proof that these jets can accelerate particles to extreme energies. Now switch to cosmic rays, which are mainly protons and atomic nuclei flying through space at high speed. They slam into Earth's atmosphere all the time. Most cosmic rays are modest in energy, but a small fraction are ultra-high energy cosmic rays, with energies up to around 10 to the 20th electron volts. Put that in plain terms, that's like taking a single proton, which is unimaginably small, and giving it the kinetic energy of a fast-pitched baseball. One particle, one nucleus carrying that much punch. When it hits the atmosphere, it doesn't just stop. It triggers a huge cascade, an air shower, where secondary particles spread out over many square kilometers, many square miles. We detect those showers with ground arrays of particle detectors and with telescopes that watch the faint glow of nitrogen in the air. The directions of these ultra-high energy cosmic rays are messy because magnetic fields in galaxies and in intergalactic space bend their paths. By the time they reach us, they don't point perfectly back to their sources. But they still tell you something crucial. Somewhere out there, nature is running particle accelerators far beyond anything we can build, using shocks in jets, magnetized environments, or other extreme physics to sling particles to absurd energies. So you now have multiple messenger channels: photons, light, from radio to gamma rays, neutrinos, and cosmic rays. On top of that, you have gravitational waves, ripples in space-time itself. The most powerful insights come when more than one channel lights up from the same event. A clean example is GW 170817 in 2017. LIGO and Virgo, gravitational wave observatories with arms 4 kilometers long, about 2.5 miles, picked up a signal from two neutron stars spiraling together and merging. The waveform told us the masses and the distance. Just about 2 seconds after the gravitational wave signal ended, gamma-ray satellites saw a short burst of gamma rays from the same patch of sky. And that wasn't the end. Optical telescopes then found a new source of light in a galaxy at exactly the distance inferred from the gravitational waves. Over days, that light changed color and brightness in a way that matched predictions for a kilonova, an explosion powered by the creation of heavy elements like gold and platinum in the debris of a neutron star merger. So for this one event, you had the gravitational wave signal telling you about the dynamics of the merger, the gamma rays revealing a short gamma ray burst, and the optical light showing the radioactive decay of newly formed elements. Different messengers, same source, all lining up. That's a full 4D story. What happened, where, when, and with what physical processes? This is why neutrinos, cosmic rays, and gravitational waves count as mysterious signals just as much as radio bursts. They're harder to detect. They require stranger detectors, kilometers of ice, arrays of tanks spread over deserts, laser interferometers with sensitivity smaller than a proton's width. And every new kind of detector opens a fresh box of problems. You see neutrino energy distributions that don't quite match your simplest acceleration models. You see cosmic ray arrival patterns that hint at structure but are smeared by magnetic fields. You see gravitational wave events with masses and spins that don't match the clean textbook binary evolution channels. Each channel reveals something unexpected. The pattern is the same. Open a new window, and the universe sends you encrypted messages in that format. At first, most of them are hard to decode. You don't know which ones are routine and which are special. Over time, you build catalogs, you see patterns, and a few events stand out as outliers that force you to adjust your models. And just when you think you've mapped out all the ways the universe can talk to you, it turns out space-time itself is ringing with signals you couldn't even detect until recently. Ripples from black holes and neutron stars colliding, stretching and squeezing distances by less than the width of a proton, but across arms kilometers long. Those are signals too, and they're about to raise the stakes again. How do you even notice a signal that stretches and squeezes space itself by less than the width of a proton over a distance of 4 kilometers, and then vanishes forever? In 2015, the upgraded LIGO detectors in the United States came online. Each L-shaped detector has 2 arms, 4 kilometers long, about 2.5 miles, with lasers bouncing between mirrors at the ends. In normal conditions, the distances between those mirrors are rock stable. The whole setup is built to detect changes so tiny they sound impossible, smaller than 1,000th of a proton's diameter. On September 14th, the system saw it. For a fraction of a second, the interference pattern of the lasers shifted in a very specific way. It looked like a rising chirp in the data, low frequency and low amplitude at first, then climbing in both frequency and strength, and then suddenly cutting off. A similar pattern appeared in both LIGO sites in Louisiana and Washington, with the right time offset for a signal passing through Earth at the speed of light. That pattern matched what general relativity predicts for 2 black holes, each with tens of times the sun's mass, spiraling toward each other, radiating energy as gravitational waves, and then colliding a billion light-years away. No light was involved in the detection. No radio waves, no X-rays. Just space-time itself oscillating, changing the length of the arms by a tiny, tiny fraction, and the laser noticing that change. That was the first direct detection of gravitational waves, and it opened a completely new type of signal from deep space. The key is that the shape of that wiggle in the detector is not random. The waveform is a fingerprint. In the inspiral phase, as 2 compact objects orbit each other, they lose energy to gravitational waves. That makes them slowly spiral closer together. As they get closer, they orbit faster, so the frequency of the waves increases. At the same time, the amplitude, the strength, also rises because the system is more tightly bound and the gravitational interaction is stronger. On a graph, that looks like a chirp, a rising pitch and loudness over time, ending abruptly when the merger happens and the single object settles down. General relativity lets you predict exactly what that waveform should look like for given masses and spins. So what LIGO and Virgo do is match the data against the bank of templates. If the pattern lines up with a template for, say, two black holes of 30 and 35 solar masses, you can infer those masses, the distance, and some information about the spins. If the waveform is different, maybe shorter and at higher frequencies, it might be two neutron stars instead, or a black hole neutron star pair. So far, we've cataloged dozens of these mergers. Black hole pairs with masses from around 5 times the Sun up to close to 100 solar masses. Neutron star mergers producing both gravitational waves and electromagnetic signals. Each event is another message, encoded not in radio frequency or brightness, but in how space stretches and compresses over time. But what if instead of listening with 4-kilometer arms, you use something far larger, measured not in kilometers, but in light years? That's where pulsar timing arrays come in. Remember pulsars from earlier? Neutron stars that spin rapidly and send out beams of radio waves like lighthouses? Some of them are so regular that their pulse arrival times can be predicted to better than microseconds over years. If space-time between us and those pulsars gets stretched or squeezed by a passing gravitational wave with a very long wavelength, the pulses will arrive a little earlier or a little later than expected. You can't notice that with one pulsar alone because each pulsar has its own noise. But if you monitor dozens of pulsars spread across the sky over many years, and you look for correlated timing shifts, patterns that appear across the whole array, you can detect a background of low-frequency gravitational waves. These waves are much slower than what LIGO hears, with periods of years, not fractions of seconds. They likely come from supermassive black hole binaries in the centers of merging galaxies, slowly orbiting each other as they spiral inward. Collaborations like Nanograph and similar groups worldwide have found evidence for exactly this, a cosmic hum, a background of long-wavelength gravitational waves revealed as subtle, shared timing deviations in pulsar signals across the sky. It's not one loud event, it's a statistical pattern, a kind of noise that only makes sense as a superposition of many distant sources. All of this forces you to rethink what mysterious signal even means. For most of human history, signals from space meant light, maybe later radio waves. If something didn't show up in that electromagnetic window, it might as well not exist for us. Before 2015, gravitational waves were a theoretical prediction, not a tool. Before pulsar timing arrays reached their current precision, the low-frequency background was just a concept. Now, black hole mergers are as real as supernovae in our catalogs. Neutron-star collisions are not just gamma-ray bursts, they're gravitational wave chirps, plus kilonova flashes, plus neutrinos in principle. Supermassive black hole pairs, which would be hard to see directly, show up as a background pattern in pulsar timings. We didn't change the universe, we just added new senses. That has a sharp implication for today's and tomorrow's weird signals. Sometimes something looks strange or impossible not because it's exotic, but because you're only seeing one slice of it. You might catch the radio flash but miss the gravitational wave. You might see the neutrino but not the gamma rays. Or there might be entire forms of radiation or particles that we haven't learned how to detect yet, carrying information we are currently blind to. So when you see a single unexplained spike in radio, or an odd pattern in X-rays, or a neutrino that doesn't fit any known model, there are two possibilities. Either it's something new in the physics we already know, or it's just one part of a multi-messenger event that we only partially detected. The truly deep mysteries might be the ones where years later we realize, oh, that thing we saw here in radio, and that other thing we saw there in neutrinos, and that tiny gravitational wave hint were all the same event. And there's another uncomfortable angle. Once you can hear space-time itself and see how violent the universe is, black holes merging, neutron stars smashing together, supermassive black holes humming in the background, it becomes very clear that extreme, precise, and powerful signals do not require technology. Nature does all of this by default. So the obvious next question is, if the universe can imitate what we once thought only technology could do, how do you design a search that is not just looking for big and bright or regular and clean, but specifically for the fingerprints of deliberate engineering, technosignatures, hidden inside this storm of natural signals? How do you tell the difference between a planet that just has chemistry and weather and a planet where something is actually building tools and broadcasting on purpose? Most of the time when people talk about life in the universe, they talk about biosignatures, things like oxygen and methane in an exoplanet's atmosphere, in combinations that are hard to get without biology. That's one level of search. Is there life at all? Technosignatures are the next level up. Is there technology? Instead of just looking for weird air, you look for things that physics allows but nature almost never makes on its own, unless someone is engineering something. That can mean a lot of different signals. Classic ones are radio beacons, narrow band tones on specific frequencies. It can also mean laser pulses, short flashes in optical or infrared. It might show up as excess waste heat on certain wavelengths if a civilization is harvesting a lot of energy and dumping it as infrared. It could even be unnatural chemical pollutants in a planet's atmosphere, compounds that only appear in industrial processes. Right now, the most mature technosignature searches are still in radio. Breakthrough Listen is a good example. It uses big telescopes like the 100-meter Green Bank Fish in the US, about 330 feet across, and the Parkes telescope in Australia, 64 meters, about 210 feet, to scan millions of stars over wide chunks of the radio spectrum. They're not just poking randomly, they focus on bands where interference on Earth is manageable and where the physics is good for long-distance transmission. Once you start recording that much radio data, petabytes of it, you need rules for what looks artificial. That's where narrowband and Doppler drift come in. Natural sources, like gas clouds or synchrotron emission from electrons in magnetic fields, usually produce broad spectra. Their power spreads over thousands or millions of hertz. In contrast, a radio transmitter that's designed to be efficient can concentrate power into a very narrow band, sometimes just a few hertz wide or even about 1 hertz. That's a sharp spike in the spectrum. So one strong artificial flag is, do you see a very thin continuous line at some frequency, say 1.5 gigahertz, that stands way above the background? If that line also drifts smoothly in frequency over time in a way that matches orbital motion or rotation, it starts to look even more engineered. For example, a transmitter on a planet that rotates and orbits its star will have its frequency slowly shift because of the Doppler effect as it moves toward you and away from you. That drift should be smooth, not random. Algorithms go hunting for exactly that. Needle in the haystack features. They scan the spectra for ultra-narrow peaks, track them over time, measure drift rates, and try to separate them from known sources of interference, like satellites and local electronics. This is not something a human can eyeball in real time. It's machine work over huge datasets. Every now and then, one of these searches turns up something that passes the basic filters and looks a little too clean. That happened with a candidate named BLC1. Between 2019 and 2020, Breakthrough Listen was observing Proxima Centauri, the closest star to the Sun, about 4.2 light-years away, roughly 40 trillion kilometers, about 25 trillion miles. In the data, they found a narrowband signal near 980 megahertz that seemed to be coming from that direction. It had a stable, clean tone, and there was some apparent drift. This was exactly the kind of thing you pay attention to. Nearby star, plausible drift, quiet part of the band. For a while, BLC1 sat in a gray zone. Not confirmed, not dismissed. The team did what you're supposed to do. They threw analysis at it for months. They checked other directions in the sky, They looked at the signal behaved when the telescope wasn't pointed at Proxima Centauri. They tested whether the drift and structure could be explained by equipment or by Earth-based transmitters. In the end, the conclusion was that BLC-1 was almost certainly terrestrial interference, something on or near Earth that happened to mimic an extraterrestrial-like pattern when seen through the telescope's side lobes and the data pipeline. It was painful because signal from nearest star is a huge headline, but rejecting it was exactly the right move. The whole point of a technosignature search is not to collect maybes, it's to filter brutally until only things that survive every Earth-based explanation are left. So far, nothing has survived that filter. Radio is not the only game. If a civilization wants to send information fast, tightly focused, and hard to confuse with nature, lasers are a strong option. Some searches look for technosignatures in the optical band by hunting for extremely short pulses on nanosecond timescales, billionths of a second. A megawatt-class laser focused through a good telescope and aimed directly at us could outshine a star for that tiny instant. Instruments with fast photodetectors can watch stars and look for single photon spikes that line up in time in a way that is very unlikely to be random noise. You can't watch millions of stars at nanosecond resolution with huge telescopes all the time, so these projects are still limited in scope. But they prove the principle. If someone out there is pinging us with short, bright laser pulses in the right direction at the right time, it is technically possible for us to notice. So where does that leave us after decades of radio SETI and newer optical searches? The honest answer is with a null result. Every credible candidate has looked promising, narrowband radio lines, odd drifts, weird patterns, has, under more detailed investigation, washed out as interference, hardware quirks, or natural phenomena. That can feel disappointing, but it is still real information. It tells you that in the parts of parameter space we've actually checked, certain frequency bands, certain time windows, certain distances, there are no loud, obvious beacons aimed right at us, at least not above our current sensitivity thresholds. It also tells you that if civilizations are out there, they are either rare, quiet, not using these channels, or simply not transmitting in our direction at the times we've been listening. This feeds straight into things like the Fermi paradox, the tension between the universe is big, there should be many habitable worlds, and we see no clear evidence of anyone. A no result doesn't prove we're alone, but it pushes models toward two broad options. Life and technology are rare or short-lived, or we are still at the very beginning of the search, with a tiny sample and primitive tools compared to what will exist in a few centuries. And remember, everything you've seen so far in this story, pulsars, magnetars, FRBs, the CMB, neutrinos, gravitational waves, the universe is fully capable of producing precise, powerful, and exotic signals without any engineering. So whatever technosignature you claim to see has to be not only the peryton test, not only the interference test, but also the could nature do this test using all the extreme physics we already know. That is why the bar is so high, and why we keep ending up with not yet. But while the searches chase the artificial, the hardware they build for that work ends up discovering more and more weird natural weirdness. New telescopes, wider bandwidths, faster detectors, and new algorithms don't only look for technology, they also expose classes of signals we didn't even know existed, like fast radio bursts. So the next step is to look at the tools themselves, at how every major upgrade in our instruments has exploded the number of strange signals we see, and how future projects like the Square Kilometre Array, combined with smarter software and AI, are almost guaranteed to dump an even bigger load of "what is that?" events into our laps. How much of the universe's weirdness have you missed just because your gear wasn't good enough to notice it in the first place? Look at what happened with FRBs. Before CHIME, fast radio bursts were rare, strange events, a handful discovered over years, each one a big deal. They look like exotic, one-off explosions. Then CHIME turned on, and that picture collapsed almost overnight. CHIME sits in British Columbia. It doesn't look like a classic round dish. It's 4 long cylinders, each about 100 meters long, roughly 330 feet. It does not steer mechanically. It just sits there and lets Earth's rotation sweep the sky overhead. The steering happens in software. Digital beamforming takes the signals from hundreds of antennas and combines them into many simultaneous beams, covering a huge stripe of sky from north to south every day. 2 numbers change the game: sensitivity and field of view. Sensitivity tells you how faint a source you can detect. Improve that, and you start seeing weaker, distant bursts that older telescopes just missed. Field of view tells you how much sky you're watching at any given moment. Make that large, and you catch more rare events simply because you're monitoring a bigger target. CHIME has both good sensitivity across 400 to 800 megahertz and a massive field of view. Multiply those, and suddenly you're not finding a few FRBs per year, you're finding them constantly, hundreds per year, then more. That tells you immediately that FRBs are not rare fireworks. They're a common feature of the radio sky, happening probably tens of thousands of times a day across the full sphere. You were just blind to most of them before. That's the pattern new hardware gives you. It doesn't gently update your picture, it flips it. Something you thought was rare turns out to be everywhere once you build the right machine. But once you start catching that many bursts, the next step is, how much detail can you actually see inside each event? That's where time resolution comes in. If you sample your data every millisecond, an FRB is just a sharp spike, maybe 2. You know when it arrived, you know roughly how strong it was, you can measure dispersion, but that's it. Push the time resolution down to microseconds, a millionth of a second, or even nanoseconds, and a simple spike turns into a structured pattern. Suddenly you see subbursts, multiple peaks within that 1 millisecond, spaced by tens or hundreds of microseconds. You see them drift in frequency over time, like the active part of the burst is sliding downward or upward across the band as it unfolds. You see fine changes in polarization, how the electric field direction rotates during the burst. All of that structure is information. It tells you about the size and shape of the emitting region, about how the plasma around the source is arranged, about whether the radiation is being bent or scattered on its way out. When you're resolving features on microsecond scales for a region that might only be a few hundred kilometers across, a few hundred miles, you're effectively doing remote sensing of a tiny bubble of plasma around some compact object in another galaxy, using nothing but the timing pattern in a brief radio flash. So your question shifts from, did a burst happen, to what exactly did the burst do microsecond by microsecond? That's a much stricter test for any model. Then there's frequency coverage. Older receivers often focus on relatively narrow chunks of the spectrum. Modern wideband receivers can cover hundreds of megahertz, sometimes close to a full gigahertz in one shot. That changes what you can ask. With wideband data, you can track the dispersion across the entire band. You can fit the delay curve very precisely and see if it follows the expected law for propagation through a cold plasma, or if there are deviations that hint at more exotic conditions. You can see spectral cutoffs, places where the burst suddenly drops out at low or high frequencies, which might tell you about absorption in the surrounding medium, or some limit in the emission process itself. You can also measure scattering tails, the way a burst gets mirrored out at lower frequencies because it has bounced off clumps of plasma along the way. Those tails tell you about turbulence in the gas, about whether the signal passed through a dense region near a galaxy or a more diffuse part of the intergalactic medium. So instead of a yes-no question, was there a signal, you're asking, how did the signal stretch, smear, and twist as a function of frequency, and what does that say about the path it took? That's a much richer data set. Now, push all of that forward to what's coming with the Square Kilometre Array, the SKA. The SKA, being built in Australia and South Africa, is designed to have about 1 square kilometer of effective collecting area, roughly 0.4 square miles. Think about that as taking a whole city block and turning it into one giant ear. At that scale, faint sources that are currently invisible become detectable. You can pick up weaker FRBs from much farther away, maybe from earlier epochs of the universe when galaxies were younger. You can map neutral hydrogen over vast volumes, tracing the cosmic web in detail. The SKA won't be a single dish. It will be a swarm of dishes and antennas spread over many kilometers, tens to hundreds of kilometers in some configurations. That gives it both raw collecting power and high angular resolution. It can pinpoint where a burst came from much more accurately, down to small regions inside galaxies, while still having the sensitivity to catch very faint events. Combine that with fast sampling and wideband coverage, and you get an instrument that doesn't just confirm what CHIME and others have already seen, it pushes into new parameter space. Lower fluxes, higher redshifts, finer time frequency structure. That's where genuinely new classes of signals tend to hide. You might find FRBs with completely different properties, longer bursts, ultra-short bursts, bursts with unusual polarization or frequency behavior that don't fit magnetar models at all. You might find a population of slow, faint radio transients that we've been missing, sources that brighten and fade over seconds or minutes with patterns we haven't noticed. You might see the radio signatures of phenomena we've only theorized about, like exotic compact objects or rare stages in stellar evolution. And it's not just the SKA. Every new instrument in every band brings the same story. Wider fields, deeper sensitivity, faster response, broader spectral coverage. Each time you go from, we have a few examples of this odd thing, to we're suddenly overwhelmed with variations of this thing, and some of them don't fit our categories at all. That's the real role of new hardware. It doesn't just increase your sample size, it forces you to expand your idea of what's possible. It takes something that looked like a one-off anomaly and reveals it as part of a much bigger pattern. It also exposes the outliers, the events that still don't make sense even after you've reclassified everything else. Those are the ones that push your physics. But there's a catch. As your instruments get better, the data volume explodes. CHIME already produces more data than humans could ever inspect by hand. The SKA will go far beyond that. You get petabytes of time series and spectra every year. Somewhere inside those datasets are the rare signals that break your models, maybe even the first true technosignature. Most of the rest is ordinary noise and known classes of sources. So the pressure shifts. You're no longer asking, can we detect these signals? You're asking, how do we find the rare, truly strange ones fast enough before they get buried? And how do we make sure we're not training our systems to ignore exactly the anomalies we care about most? How do you actually find the one signal that changes everything when it's buried inside petabytes of mostly boring data? Modern sky surveys don't give you a few neat plots, they dump mountains of time series and spectra onto your disks. Radio telescopes, optical surveys, X-ray monitors, all of them are recording at high time resolution across wide frequency bands for huge chunks of the sky. You end up with data volumes in the petabyte range, thousands of terabytes, and that's just one project. A human can stare at waterfall plots, those time frequency diagrams, all day and still miss rare, subtle patterns. You'll catch the obvious bright bursts, the clean periodic signals, but a millisecond event that just barely rises above the noise, or a weak, slightly curved dispersion track, or a strange polarization signature that doesn't match any template will slide past your eyeballs without leaving a mark. There just isn't enough attention to go around. So teams started doing the only thing that scales. They train machine learning models to do the first pass. Convolutional neural networks, the same kind of architecture that can tell cats from dogs in photos, are repurposed to classify pulsars, FRBs, radio frequency interference, and generic noise. You feed them labeled examples, show them thousands of known pulsars, thousands of clean FRBs, thousands of obvious RFI cases, and they learn to map new inputs into those categories. Now, instead of a human flipping through every candidate by hand, the system flags likely pulsars, likely FRBs, likely junk. The human steps in later on a filtered list where the priorities are already sorted. Without that, half of these big surveys would just drown in their own output. And it's not just about live data. People have gone back to old archives with new algorithms, and the results are a bit embarrassing in a good way. There are pulsars and FRB candidates that were first noticed by neural nets years after the original observations. The telescope saw them in real time, wrote the data to disk, and then the event vanished into a catalog because it didn't trigger any simple threshold or rule. Later, a trained model scans those old files, looks at the same plots, and says, this pattern right here looks like a pulsar, or this curve looks like a dispersed burst. In several cases, that was correct. The algorithm picked up a periodicity, a dispersion signature, or a shape that handcrafted cuts had ignored. That is literally your own software telling you, you missed this back then. It proves that your tools, not the universe, were the limiting factor. That's the upside of AI in this field. It sees structure where you saw noise, but there's a hard downside you can't ignore. If you only train your models on what you already know, pulsars, FRBs, standard types of RFI, clean Gaussian noise, then the system becomes very good at reinforcing your current categories. Anything that doesn't look like those classes might get shoved into noise or dropped entirely. In other words, you risk building a machine that is excellent at finding the familiar and blind to the truly new. To avoid that, astronomers don't just build classifiers, they also build anomaly detectors. Instead of asking, which bucket does this fit in, they ask, how far away is this from any known bucket? You can think of every signal as a point in a high-dimensional feature space, where the axes might be things like pulse width, dispersion measure, polarization fraction, spectral index, modulation patterns, and so on. Known sources form clusters in that space. Anomaly detection systems highlight points that sit far away from all those clusters. They don't tell you what the thing is. They just say, this doesn't look like anything in the training set. That's exactly where the mysterious signals of tomorrow are likely to sit, out on the edges, in the tails of the distribution, in regions your classifier doesn't understand. But that makes your problem sharper, not easier. Now you have lists of outliers. Some are just garbage, artifacts from the instrument, bugs in the processing pipeline, or rare forms of interference. Some might be new astrophysical phenomena. A few, in the most optimistic scenario, might be genuine technosignatures. Your job is to decide which is which, and you're leaning on AI to even generate that short list for you. This is where the stakes jump. As we hand more and more of the first pass filtering to algorithms, we're trusting them to decide what deserves human attention. A real civilization-level technosignature, if it ever shows up, it might not arrive as a dramatic wow printout or a live alert the whole field sees at once. It might show up first as a single entry in a database, flagged with a tag like high score anomaly, or as a small, tight cluster of weird points on a TSNE plot that only a few people ever look at. You could, in principle, have a situation where the first evidence that we are not alone is quietly sitting in a table marked as unclassified transient, because the model didn't know where to put it and no one has had the time to review that segment yet. That is not science fiction. That's the logical endpoint of combining giant instruments, huge data streams, and limited human review capacity. So now you're in a race against your own tools. You need algorithms that are good enough not to bury the truly strange under a mountain of false positives, but not so rigid that they erase anything that doesn't match the training labels. You need pipelines where anomalous events are logged, cross-checked across instruments, and revisited, not just thrown away. And you have to accept the slightly disturbing idea that some of the most important signals we'll ever see, whether they're new classes of magnetar flares, exotic compact objects, or an actual artificial transmission, will first be seen not by you, but by a pattern recognizer that has no idea what important even means. That's the new landscape. Giant telescopes pouring out data, machine learning watching for patterns, anomaly detectors flagging outliers, humans trying to keep up. Together, they're turning what used to be a quiet, empty universe into a crowded, noisy one, full of structured signals across many channels. So the final step is to pull back and look at the whole picture. Once you add up all these messages, radio bursts, pulsars, magnetars, microwaves from the Big Bang, neutrinos, cosmic rays, gravitational waves, plus whatever AI helps you uncover next, what does that do to your story of the universe and where you fit inside it? 100 years ago, radio astronomy basically didn't exist. If you looked up, you had stars, planets, and a vague idea of nebulae. No radio sky, no gamma ray sky, no gravitational waves, no fast radio bursts. Static was just something on your early radio set that you tried to tune away. Now, that static is structure. You've got the cosmic microwave background giving you the oldest signal, the afterglow from when the universe was only a few 100,000 years old. That's the baseline, a 2.7 Kelvin microwave bath filling every direction, setting the stage for everything that comes after. On top of that, you've got pulsars, neutron stars about 20 kilometers across, about 12 miles, acting as precision clocks scattered across the Milky Way. Their radio pulses arrive so regularly that you can time them to microseconds and use them to measure gravitational waves, probe the interstellar medium, and test the behavior of ultra-dense matter. Then you have FRBs, millisecond sirens from deep space, flashes that carry as much radio energy in a thousandth of a second as the sun emits in days. They're not rare outliers anymore. They're happening across the sky, probably tens of thousands of times per day, and you catch a tiny fraction with instruments like CHIME. Gravitational waves are the space-time tremors, ripples from black holes and neutron stars colliding, changing the lengths of 4-kilometer, 2.5-mile interferometer arms by less than a proton's width. You don't see these with eyes or radio, you feel them as tiny correlated shifts in distance. Neutrinos and cosmic rays are your invisible arrows. Neutrinos, almost massless, weakly interacting particles, carry direct information from dense environments, like supernova cores and black hole jets, going through light years of matter as if it's almost not there. Ultra-high energy cosmic rays, single protons or nuclei with energies up to about 10 to the 20th electron volts, tell you there are natural accelerators out there that make the Large Hadron Collider look small. Put that together and empty space stops being empty. It becomes a dynamic, chattering network with different messengers encoding different aspects of the same violent universe. Every part of the spectrum, every particle type, every wave channel is carrying structured signals. The moment you see it that way, every new anomaly stops being just a curiosity and becomes a test of physics. Take FRBs. Their dispersion measures, how much the low frequencies are delayed relative to the high ones, tell you how much ionized gas the burst has crossed. If those numbers systematically disagreed with your models of the Milky Way's gas and the intergalactic medium, you'd have a problem. Either the plasma content is wrong, or your understanding of how radio waves travel through it is off. So far, FRB dispersion roughly agrees with a universe filled with thin, ionized gas in the amounts you expect. That reinforces your picture. But any big deviation in a new class of bursts would be a hint of new physics, or at least new astrophysics. Gravitational waves are another sharp test. General relativity tells you exactly how a binary black hole's waveform should look, from the early in-spiral to the merger to the ring down of the final remnant. If you saw a signal with clear systematic differences, wrong frequency evolution, unexpected echoes, a ring-down pattern that doesn't match a simple black hole, you'd be forced to ask whether gravity behaves differently at extreme curvature, or whether the objects involved aren't standard black holes at all, but some exotic compact objects. Neutrinos from blazars and other accelerators test how particles gain energy in jets and shocks. The spectrum of neutrino energies, the angles they arrive from, and how often you see them all have to match models of how protons and nuclei are accelerated and interact. If those models fail badly, you might have to consider new particles, like dark sector cousins of photons, or new interactions that don't show up at lower energies. In other words, each strange signal isn't just, we saw something weird, it's, we got another data point on whether our equations actually hold under extreme conditions. Most of the time, the universe says, yes, your math still works. Sometimes it nudges you toward gaps you didn't know were there. Now think about what happens when you stop treating these signals one by one and instead use them as probes, shooting through the galaxy and the space between galaxies. You start doing tomography of the universe. Every radio signal that passes through the Milky Way gets distorted by the gas and magnetic fields it crosses. By analyzing dispersion, scattering, and polarization for thousands of pulsars and FRBs in different directions, you can map out the electron density and magnetic field structure of the galaxy. That's galactic weather, the large-scale state of the plasma your own solar system is embedded in. It matters for everything, from cosmic ray propagation to how stars form. Go beyond the Milky Way, and FRBs start probing the cosmic web itself. The space between galaxies isn't uniform. Matter clumps into filaments and nodes that can span tens of megaparsecs, tens of millions of light years. As FRBs pass through those filaments, their signals pick up extra dispersion and scattering. If you know the redshift of the host galaxy and the Milky Way's contribution, the leftover dispersion tells you about the gas in the web. With enough bursts, you can statistically reconstruct how baryons, normal matter, are distributed on huge scales, including the missing matter that's hard to see directly in X-rays or optical light. So FRBs are not just mysteries, they're tools. Pulsars are not just weird clocks, they're beacons that let you measure gravitational wave backgrounds and galactic structure. The CMB is not just leftover radiation, it's your global boundary condition. Every signal you catalog becomes another probe line through the universe, another constraint on how matter, energy, and space-time are arranged. Then there's the question that sits behind most people's curiosity about mysterious signals in the first place. What does all of this say about life and intelligence, about whether there is anyone else transmitting? Here's the blunt situation. You've seen millions of astronomical signals across radio, optical, X-ray, gamma ray, neutrinos, cosmic rays, and gravitational waves. You've logged catalogs full of pulsars, magnetars, FRBs, supernova, gamma ray bursts, blazars, black hole mergers, neutron star mergers, and more. You've run targeted technosignature searches on nearby stars, on interesting systems like Tabby star, on regions around the galactic plane, using big dishes and sensitive receivers. So far, you have 0 confirmed technosignatures, no narrow-band radio signal that survives all interference and natural explanations, no repeating pattern that screams engineered, no obvious waste heat excess that demands megastructures, no spectral lines that clearly come from industrial pollutants. That null result isn't the final word, but it does mean something. At minimum, it tells you that in the volume of space and range of frequencies you've actually checked with reasonable sensitivity, there are no civilizations broadcasting loudly and continuously in simple ways that we'd easily pick up. Whatever is out there is quiet, rare, short-lived, using channels you're not monitoring, or simply not pointed in your direction during the slices of time you've observed. The only reason you can even say that with a straight face is because of decades of listening. Because you have built the hardware, cataloged the natural signal zoo, and pushed down the noise enough to be confident that we didn't see anything is not the same as we never looked. So you end up with a strange contrast. On one hand, the universe is louder and more structured than anyone in 1920 could have imagined. It's packed with extreme objects, sending out precise, powerful signals and all kinds of radiation and particles. On the other, when you specifically look for deliberate technology, everything credible has washed out so far. Natural weirdness everywhere, confirmed technology nowhere. That tension sets you up for the final question. If the sky is this full of signals, if every new instrument upgrade unlocks another class of phenomena, if AI is now combing through petabytes of data in real time, why do you keep ending up in the same place? More mysteries, more natural extremes, but still no clear artificial beacon. And deeper than that, given everything we've seen and everything we haven't, what is the real reason we keep receiving mysterious signals from deep space? And why should you expect that pattern to continue and even get more intense in the years ahead? So after all of this, why do mysterious signals from deep space keep showing up in the news instead of dying off as our understanding improves? First reason, your instruments just will not stop getting sharper. Every time you gain a factor of 10 in sensitivity, every time you open a new waveband, every time you add a new kind of detector, you peel back another layer of the sky. A radio telescope that can see sources 10 times fainter is not just seeing the same stuff but dimmer, it's seeing an entirely new population that used to sit below the noise floor. Same for field of view. When you go from staring at one tiny patch of sky to watching a huge stripe, like CHIME does, you turn rare events into routine ones. FRBs went from, we have a strange one from 2007 to we're logging hundreds per year just by changing how much sky and how often we look. That's not the universe changing, that's us finally paying attention at the right scale. Then you add new channels. 100 years ago, radio astronomy did not exist. A few decades ago, gamma ray bursts were still a surprise. Gravitational waves have been a thing we can actually measure for only about 10 years. High-energy neutrino astronomy with instruments like IceCube is just over a decade into serious operation. Pulsar timing arrays are only now starting to resolve a gravitational wave background. Optical surveys that scan the whole sky every few nights, like the ones leading up to LSST, are even more recent development. Set that against the universe that is about 13.8 billion years old. If you compress that into a single year, your entire history of radio astronomy takes up less than the last second before midnight on December 31st. Your gravitational wave work is a fraction of that second. In that sense, you're fumbling around in the first microsecond of real multi-messenger observation. From that perspective, it would be shocking if you did not have lots of mysterious signals. You've just started listening with decent equipment. You're still building catalogs, still figuring out which classes are common and which are rare. A future civilization with 1 million years of data, instruments spread across our planetary system, and detector types you haven't even imagined yet, will probably look back at this era and think, of course they were constantly surprised. They were basically guessing from a few early snapshots. So the final piece is, the mystery rate stays high because you are early and your tools are improving fast. At the same time, that combination guarantees a constant stream of this shouldn't be possible events that later turn into, okay, now we understand it, once you collect more data. Now tie it all together. Right now, while you're watching this, the sky above you is busy. Somewhere overhead, a millisecond radio flash is crossing intergalactic space, carrying the energy of days of solar output from a galaxy billions of light years away. A high-energy neutrino is flying straight through Earth, through your body, through thousands of kilometers of rock, as if it's almost not there. A gravitational wave from two distant black holes or neutron stars is stretching and squeezing distances on Earth by less than the width of a proton, over 4-kilometer interferometers, and your detectors are quietly recording that pattern. Almost all of those signals will pass by unnoticed. They won't line up with a telescope beam. They won't hit a detector at just the right time. They won't cross a threshold in some algorithm. They'll just be part of the background frenzy the universe has been running since long before there were eyes or radios here to notice it. But some of them will land exactly right. They'll show up in the data. They'll survive the RFI tests. They'll pass the peryton checks. They'll resist all the obvious natural explanations for a while. They'll force you to add a new line to the list. Pulsars, magnetars, FRBs, gravitational wave mergers, neutrino flares, something else. And every time that happens, you'll look at the plots, you'll look at the model that fails, and you'll end up saying the same thing again. This isn't what we thought the universe was capable of. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.